So before we get started on the actual thermodynamics side of it, I'd like to cover the discrepancies between pounds of force, pounds of mass, and slugs, and why it's so confusing. The metric system doesn't have this problem because of how it was invented, why it was invented, and what people were thinking when they invented it. So back before the metric system, most systems just considered how heavy something was. No one thought of making a distinction between mass and weight. But once Newtonian physics came around and we started understanding that mass is a significant contributor, that's when slugs were created retroactively in the Old English system. So, force is mass times acceleration, so what we have to do is divide force by acceleration. To get slugs, you take the weight of something on Earth and divide by the acceleration due to gravity. So we get this unusual unit where we have to work backwards from weight to figure out what the mass is. So one slug weighs 32.2 pounds on Earth. Now, to change that into something that people were more familiar with, pounds of mass were created retroactively, and so you take the number of slugs that something weighs and you multiply it by the acceleration due to gravity on Earth. But you remove the dimensions of acceleration, feet per second squared. And so you end up with pounds of mass and pounds of force showing up as exactly the same when you weigh them on Earth. That was supposed to make it less confusing, but once you have those very intuitive numbers and you actually have to do something with them, you have to go through the whole mess of converting it backwards. So in the metric system, they started with mass. They started with kilograms. And then they considered weight in newtons. But newtons are also unintuitive. So there's a process in the metric system that was done backwards to create a stand-in unit for weight and forces called kilograms of force, kgf. Now it's used a lot for evaluating the thrust of rockets that are taking things up to space. Right? So you can look at the kilograms of force that the rocket is capable of outputting and comparing that to the kilograms of mass that your payload weighs, and you can use that to evaluate if your booster is strong enough, if your engines are strong enough. And we also find it in a very familiar place, the grocery store. That's how you're able to measure your food in grams and kilograms. And it's also used interchangeably when you're asking how heavy is something and people say, oh, it weighs 20 kilograms. That's kilograms of force. So, an interesting history lesson to consider here, and yes, this is relevant to our topic material, is understanding what the entire study is about. And so, back in the day, there was this notion that heat was its own unique thing, so an entire field of study was built around it. The name thermodynamics means the study of how heat moves and changes. But they thought that heat was a type of fluid. Eventually, they realized it's a form of energy. And as such, it's connected to all the other forms of energy. It's connected to work, it's connected to potential energy, it's connected to light, it's connected to all sorts of things. And so, it eventually ballooned and morphed into this new field of study, hence the asterisk on the name thermodynamics. It's the study of energy. So if you're wondering why we're asking how efficiently we can pump water up a hill from one reservoir to another, or how efficient electric motors are, or how efficient a pump is, it's because we're looking at the energy, the utilization of it, the efficiency of it, and this allows us to figure out where the rest of our energy is going. And it's kind of the whole point, so it's very important to approach each thermodynamics problem with energy in mind.